Okay, we're going to continue on here. We have just a little bit more to talk about in terms of what we've been talking about, which is kind of a really kind of a stoichiometry and different types of stoichiometry. So last time we got into really kind of solutions a little bit, and obviously solution stoichiometry. And remember that the most common unit of sort of concentration is molarity, which is moles per liter. And again, you can think of molarity as we talked about, sort of a formula that you can rearrange, and we do use it a lot, especially with stoichiometry problems as well. We could solve for liters, which is our moles divided by molarity. We could also start with our moles, our solve for our moles, which is liters times molarity. So that's a really important thing that we talked about as well, which is, again, when you're using molarity by itself, sort of with volume, you want to make sure that the volume's always in liters, because that's probably what you're looking for, again, is moles. Remember that if you do sort of multiply milliliters times molarity, you get what are known as millimoles, which are okay in a sense, but you're most likely shooting for moles. So if you don't recognize that you are actually in millimoles, you'll be off by a factor of 1,000, and obviously you will get the wrong answer. So always a pretty safe bet, just straight molarity and volume. Make sure it's in liters. That way you get moles, which, like I said, is pretty much what you're most likely looking for. We talked about dilutions, which is basically when you add more solvent to a solute, and there is a dilution equation, which is M1V1 equals M2V2. And this is sort of usually before the dilution, is usually after the dilution. Remember also there's sort of a generic version of this, C1V1 equals C2V2. It's the same deal. Again, you can use any type of concentration unit you want in there. This is the one place where you can, if you like, leave the volume in milliliters. As long as the milliliters are both on each side, everything will work out okay. Or if it's molarity, milliliters, and molarity, when you solve for volume, it'll still be in milliliters because the millis will cancel each other out. Other than using this equation and you're using molarity and volume, you should definitely always convert it to liters so you'll be in the right units that you're most likely looking for. We got into solution stoichiometry, which is really the same sort of 4 steps that we've been doing for any type of stoichiometry problem, which is balance equations, convert to moles, do your mole to mole relationship, and then kind of moles to some other unit. And really, kind of the two places where slightly different solution stoichiometry problems is usually up front, instead of using grams of molar mass to get the moles, a lot of times we do use the liters, is moles divided by molarity. Also, on the back end of the calculation, we will also sometimes use the same thing, or we will maybe just solve for molarity as well. So those are two sort of common endings, along with the normal common ending of maybe getting to grams as well. So these are sort of some variations on it. As we also saw, you can have a limiting reagent type situation as well in any type of stoichiometry problem, even if it's a solution stoichiometry problem. We'll talk about gas in a second in the next chapter. But you always want to also make sure, again, if it's a limiting reagent problem, that you do figure out the limiting reagent, do some type of calculation, and then do the problem accordingly. Um, that brought us to more specifically titrations, and they're really, again, sort of titrations are basically solution stoichiometry problems. The process titration we also talked about that you use a burette. The idea of titrations is you usually will know something about one of the solutions involved in titration, and you will have like an unknown aspect of the other solution. And usually we titrate until we get the reaction to kind of go to completion, which is usually in an acid-base titration, for example, what's known as the equivalence point. And in that equivalence point is where the moles of acid equal to moles of base. When you're doing an acid-base titration, that's sort of the end of the reaction, in a sense, happening. And we could use sort of solution stoichiometry to figure out things like the volume that's maybe needed to reach the equivalence point. We could also figure out molarity. We could also figure out molar mass as well. for an unknown acid or solution. So there's a lot of things you can figure out with titration, but ultimately they are still really titration type problems. They're still solution stoichiometry problems where you kind of follow those steps. Any questions on any of that stuff there we talked about last time? All right. Then let's talk about a few other concentration units as we kind of got into solutions and stuff like this. And another sort of important concentration unit is percent by mass, or sometimes referred to as mass percent, and sometimes abbreviated percent m/m. And the percent mass to mass is equal to the mass of the solute, which is the smaller part of the solution, divided by the mass of the solution times 100%. Now, the really important part of this calculation is really the bottom part here, and that is the mass of the solution. Remember that a solution is made up of two things, made up of the solute, which is the smaller part, and the solvent. And you do want to make sure that you get both of those guys when you do that. And the reason it's really kind of important, these type of problems is in percent mass to mass problems, they oftentimes will give you that information separate. So they'll kind of give you the mass of the solute, they'll give you the mass of the solvent, and it's a very common mistake that people just kind of go with just the mass of the solvent by itself, rather than adding them together. So I would say out of all the concentration units, this bottom part of the calculation here is something that you oftentimes will need to do. Figure out the solute and the solvent, make sure you add them together to get the mass of the solution. If you have a 4.5% by mass, say sodium chloride solution, a lot of times if you're given sort of the percentage by mass, it's a lot of times easier to use it in a calculation by just kind of turning it into a conversion factor. And since it is a percentage, like most times that we're dealing with percentages, 100 is sort of what we assume. So what that would mean, for example, is if you had 4.5% by mass sodium chloride, that would mean you would have 4.5 grams of sodium chloride in 100 grams of solution. And that's a nice little kind of conversion factor that you could turn this percentage into and use it in a dimensional analysis problem. You could also flip it around and use it the opposite way, 100 grams of solution. You would have 4.5 grams of sodium chloride. So I would recommend, kind of like what we talked about when we did molarity, that you get rid of kind of the big M and you see both of the units and you take a more dimensional analysis approach. Definitely, sometimes it's easier to kind of take a dimensional analysis approach if you're given the percentage by mass, and solve for what you need and just kind of do it that way. Again, you could also just plug and chug into the equation and it will be the same math and you could solve for whatever, you're missing. But sometimes just kind of taking a conversion factor type situation is a easier way. Now, percent mass to mass is one of a couple other sort of percent concentration. So there's a couple of others. So let's talk about those. There is percent volume to volume, like in alcohol, percent volume by alcohol. And that is the volume of solute divided by the volume of solution times 100%. And there's also percent mass to volume, and that is basically the mass of the solute divided by the volume of solution times 100%. So in terms of the three sort of percent concentration, adding the one we just saw on the previous page, our mass to mass, which is our mass of our solute, mass of solution times 100%. This guy is kind of like grams over grams. This one is sort of grams over milliliters, almost like density. And this one is usually milliliters over milliliters in terms of the units. They all usually will end up as a sort of a percentage when it's all said and done. So we just saw our 4.5% by mass sort of turning into a conversion factor. If you had 4.5% volume to volume of sodium chloride solution, that would mean you had 4.5 milliliters of sodium chloride in 100 milliliters of solution. Or again, you could flip it around and go the other way, 100 milliliters of solution over 4.5 milliliters of sodium chloride. You can also have 4.5% mass to volume sodium chloride, and that will give you 4.5 grams of sodium chloride in 100 milliliters of solution. Or again, you can use it as a conversion factor the other way, 100 milliliters of solution gets you 4.5 grams of sodium chloride. So again, these are ways that you could turn these percentages into sort of usable conversion factors, and you want to make sure that you sort of do that. It's a lot of times a little bit easier, but you could also, in each of these cases, just kind of plug and chug into these equations as well and solve for whatever's missing. This is also why when we're talking about sort of the dilution equation, where sometimes people use C1V1 equals C2V2, although molarity is, again, the most common unit of concentration. That's why most people roll with this equation. You technically could use any of these sort of concentrations in that equation as well, and it'll come out the same. So you can use dilution in any of those concentration units. Any questions on that there? All right, so why don't you try one here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the percent? Take a look. We have a solution prepared by taking 2.5 grams of calcium chloride with 50 grams of water. So once again, this is the smaller part of their solution, which would be our solute. This water here would be our solvent in this case, which is the larger part. So our percent mass to mass is equal to the mass of the solute divided by the mass of the solution times 100%. So in this case, again, we do have the mass of the solute, which is our 2.5 grams. We have our mass of our solvent, which is 50 grams. So remember that, again, the important part of this, as you can see here, they are given separate. So we want to make sure that we do add those together to get the mass of the solution. So the mass of the solution would be 50 plus our 2.5 grams, going to give us something like 52.5 grams. Now we have everything we need. We're going to take our solute, 2.5 divided by 50, 52.5 grams, times it by 100%. And that is going to get us here, looks like 4.76%. We do usually will put M/M to let people know it's sort of mass to mass percent. And you could also put what it is, which is calcium chloride. So you could use something like that if you like. Any question on that calculation? Again, a lot of times people will just go with the solvents, and you got to make sure you get them both because very commonly they are separated in these type of problems. Any questions on that calculation there? All right, so let's try another one here that we have. Let's see. Maybe there it is. Concentrated hydrochloric acid solution contains 37.2% by mass hydrochloric acid. What is the mass of hydrochloric acid that's in 35.5 grams of the solution? Okay, so once again, we are dealing with percent mass to mass here, which is our mass of our solute divided by, again, our mass of our solution and times 100%. In this case, they did give us the percent mass to mass, which is 37.2%. We also have the mass of the solution, which is 35.5 grams. And we're looking for the mass of the HCl in this particular case. So even in this problem, they did tell you it was the solution. I would know that I'm actually looking for the mass of the solute in this case. again, because the name of the solution is the solute. So if you're looking for the mass of the HCl, that would definitely be your solute. That would be how I would know, for example, that this number would be the solution part of it and not the solute, because again, we're looking for really what the solute is in this case. So you can plug and chug into here, or once again, you can take a more dimensional analysis approach, where this would mean that there are 37.2 grams of HCl in 100 grams of solution, or in 100 grams of solution, there are 37.2 grams of HCl. So if you take this more sort of dimensional analysis approach, we could take our mass of our solution, 35.5 grams of solution. We would need to use a conversion factor here on the left so the solutions cancel. Gets us 37.2 grams of HCl and 100 grams of solution. Those guys cancel, gets us 13.2 grams of HCl is basically in this particular solution. Any questions on that calculation there? Now, obviously, if you just kind of plugged and chugged into the equation, you have a similar sort of calculation. You're going to do 37.2% would equal our mass of HCl divided by 35.5 grams times 100%. And essentially what you'd be doing is multiplying the 35.5 to the other side and dividing by that, which would basically give you the exact same calculation, obviously, as above. Any questions on percent mass to mass, percent volume to volume, and percent mass to volume all really kind of work the same way? Again, they are sort of percent units of concentration. I would say probably out of the three there, percent mass to mass probably use the most, maybe volume to volume as well. But again, molarity, much more common unit of concentration. Another type of unit of concentration for solutions is actually molality, and molality is not to be confused with molarity that we talked about. Molality's abbreviation is actually a little m, and again, not for mass or anything. In this case, it's actually molality. And molality is the moles of solute over kilograms of solvent. So this is moles per kilogram of solvent. And the important part of this is, again, it is kind of used similar. So if you had a 4.50 molal solution of sodium chloride, that would mean you had 4.5 moles of sodium chloride in a kilogram of the solvent, which most likely would be water in that particular case. And again, it's also very much like molality, that if you are using it, say in a calculation, sometimes it's good to kind of turn it into the 2 units so that you can see the moles and the kilograms, you don't lose a unit along the way. So again, molality is moles per kilogram of solvent, not to be confused with capital M, which is molarity, which is moles per liter. The thing that sort of ties both of these together, if you need to kind of go from one to the other, it's actually density a lot of times is what is used to sort of tie them together, or if you need to kind of convert from one to the other, the density of the solution or substance is oftentimes used to kind of go from one to the next. So molality is a unit of concentration which I would say is not used a lot in a sense of normal sort of solution type problems. Where it is used and where we will see it a lot is towards the end of the semester when we talk about colligative properties of solutions. It's used in a number of sort of calculations that we do for things like vapor pressure lowering. Actually, it's not in that one, but actually boiling point elevation and um, freezing point depression and some other type of calculations. So we will see molality again in a couple of other chapters and some formulas. But I would say again, in terms of solutions, most of the time molarity is going to be the one, but this does pop up a little bit along the way. So why don't you try one here? Calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. We'll give you some numbers here. Carbon 12.01, hydrogen 1.008, and our good friend oxygen. Okay, so let's take a look. So here we're going to solve for molality, which again is little m. And again, that is the moles of the solute over kilograms of solvent. In this case, the water is going to be our solvent, and our C3H7OH there will be our solute, which is what we're dissolving in it. So we do need to get the moles. We have the grams of the solute. So we do need the molar mass here. So that's going to be 3 carbons at 12.01. Looks like we have a total of 8 hydrogens at 1.008. And we got 1 oxygen at 16 here in this case. And that looks like we will end up with it's like 6009 as our molar mass here from the periodic table. So we're going to use that to convert our grams into moles, which is kind of the top part that we need there. And if we do that there, 61.7 divided by 6009, like a 1.03, we'll call it moles. Once again, that is the top part that we need. We do need kilograms of our solvent. In this case, though, we have the volume of our solvent, and we do actually have the density given to us. And if it wasn't, we should know that the water density there is 1 gram per milliliter. We could use that in our density equation to figure out that the mass is volume times density, which would give us 175 milliliters times our 1 gram per milliliter, gives us 175 grams of water, which is our solvent. Remember, though, in molality, we need it in kilograms, so we need to convert it to kilograms so that everything cancels out correctly. So that is 1,000 grams in a kilogram, and that will give us 0.175 kilograms of water, or our solvent in this case. Any questions up to there? Now we have it in the correct units for the bottom part that we need. All that's left is to put it in there. So a little 1.03 moles divided by 0.175 kilograms, gonna get us there divided 0.175. Looks like 5.87, we'll call it here. Now, in terms of the units, much like molarity, they do not cancel out, so you can leave them as moles per kilogram. Or just like molarity, you can put a small m, not a big M, obviously, because that would indicate molarity. So you could do either way that you want to do it there and leave it. Any questions on molality? Once again, we will definitely see it more in sort of those colligative properties that we'll see a little bit later on in the semester. But it is a good little unit, I suppose, as well. Questions on that? All right. Now, lastly here, another thing that we will see, and we'll actually see in the next chapter as well, when we talk about gases, is mole fraction. So sometimes there's situations where maybe you want to calculate something. For example, we'll see it in the next chapter where maybe you want to figure out pressures of everybody and sort of a mixture of gases, but you really don't have enough information to sort of get to use a gas law or something like that. So another sort of helpful unit in addition was referred to as the mole fraction. And the mole fraction is abbreviated with an X. So when you see an X, that usually involves the mole fraction. And usually they'll put like whatever their mole fraction of, in that particular case. It's really like a percentage without multiplying by 100. So it's like everything but multiplying by 100. That means because we don't multiply by 100 and make it a percentage, the maximum thing that you get is 1, which is 100%. So basically, to figure out the mole fraction, you take the moles of what you're interested in, like A, and you divide it by the total moles, and that is it. And again, we don't multiply by 100 here. It's not a fraction, so you'll end up with like a point something type number. And again, when you add up all of the moles of all the components of that solution or that mixture, it should add up to 1, which would be, again, 100% of what is present. You could also do that, obviously, this would be a situation where maybe, you had a bunch of stuff floating around, A, B, C. You could do it for everybody here. This would be the moles of B divided by the total moles. Again, in this case, if you actually did something like this, you could figure out the moles of C by subtracting by 1. So 1 minus the total of those two together will also give you, in this case, the moles of C, since that's the only other one that's present. So why don't you try one here? Calculate the mole fraction of methyl alcohol in a solution composed of 0.328 moles of methanol and 0.929 moles of ethyl alcohol. We're looking for the mole fraction here of CH3OH. That would mean we need the moles of it over the total moles in this particular solution. So obviously we have the moles of this guy given to us, which is 0.328. We also have the moles of the other part of the mixture there, which is 0.929 moles. We add them together. That's, in this case, going to give us our total moles of 0.328 plus 0.929, 1.257 moles, which is our total moles. So in this case, we can take our moles of our CH3OH, which is 0.328, divided by the total moles, 12757 here. And that will get us there about 0.2609. It's basically 26% made up of this. Again, we could get the mole fraction of the other component in this case by doing one of two things, even though it didn't really ask for it in this problem. We could do the same sort of calculation. So we would take the moles of the other component divided by the total moles. And again, that's going to give us our mole fraction for our other component in this particular case, which is about 73% or so, but basically 0.7391. We also could have got there by taking 1 minus 0.2609, and that would also get us there as another way to do that, since that's the only other part of this particular mixture. Any questions on mole fraction? We will again also see mole fractions, like I said, in the next chapter in gases, and we will also see it with colligative properties as well. So does sort of pop up in a few different places along the way. Any questions on that there? Or that will be on the next exam topic-wise. So we're going to talk about a number of gas laws in here. We're going to talk about maybe some gas laws you maybe haven't seen before, and some other ideas about gases as well that maybe you haven't seen as well. So we'll also talk a little bit about gas stoichiometry, I think, along the way as we go through it. So let's talk about gases. Obviously, when we're talking about gases, we are talking about the state of matter where everybody has basically broken apart from one another. They're flying around in the container in which they are in. As they are flying around, there's numbers of collisions that occur. The collisions is basically the amount of collisions is what we associate pressure with when we talk about gases, right? We talk about gases, high pressure, low pressure, whatever it may be. The number of collisions are usually directly related to, obviously, how much pressure that you have in general. The more collisions that you have, the more pressure that you have, and the less collisions that you have with the gas molecules as they're flying around, the lower the pressure situation is. So let's talk a little bit about what substances do exist as gases under normal conditions. When we talk about kind of normal conditions, it's sort of everyday sort of conditions. It's oftentimes the standard conditions in the sense of what table values are made up and stuff like that. And that is usually refers to a pressure of 1 atmosphere, which is an ATM. and a temperature of 25 degrees Celsius. Now, under sort of normal everyday conditions, when we talk about ionic compounds, which as we know are metals and nonmetals together, held together by those really strong electrostatic attraction, the positive and negative attraction between the two ions, they usually are not found in the gas phase. That is a very, very strong attractive force that you could have. Probably one of the strongest attractive forces you could have is that opposites attract. And because of that, to try to get an ionic compound to sort of go into the gas phase, it really doesn't happen under normal conditions. It would take a very, very large amount of heat and energy to try to do that. Typically, the best that you could do sort of with an ionic compound is you could heat the heck out of it and it will just start to melt before it will actually break apart into sort of the gas phase or anything like that. Again, as you know from a lot of the experiments that we did where we evaporated off, say, the water and stuff like that, in your evaporating dish, you heated that pretty strongly. Not everything went away, not everything evaporated away. You still have the ionic part of it. Compounds still remain in your evaporating dish, even though after you hit it. Now, covalent compounds or molecular compounds, which again are held together by more sharing of electrons, they are very different behavior than, say, ionic compounds. Some molecular compounds are just gases normally, CO, carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, methane. These are all gases under normal conditions. And the vast majority, though, of molecular compounds are still really liquids and solids. The one major sort of difference between molecular compounds and ionic compounds is really sort of the ease at which you can really convert a lot of times a molecular compound into a gas versus trying to convert an ionic compound into a gas, which usually doesn't happen. The probably most common example that everybody's familiar with is our friend water. So water, which is a polar molecule, is held together, for example, in the liquid state and in all states, really, in a sense, through a very simple attraction between one water molecule and another. Is the positive side of one is attracted to the negative side of another, so the hydrogen is attracted to the oxygen side. And this is a type of interaction which is known as an intermolecular force. And an intermolecular force is the force that holds one molecule together with another. So it's how all the water molecules basically stay together. It's how one molecule interacts with another one is intermolecular forces. And those intermolecular forces, in the case of here, by the way, this is what is referred to as hydrogen bonding in the case of water, is the type of intermolecular force that's basically happening. And there's another type of force which is known as an intramolecular force. An intramolecular force is the force within a molecule that holds it together. So, for example, if you took just one water molecule, it is the covalent bonding that's happening between the oxygen and hydrogen on each side of the water molecule. That's an intramolecular force within the molecule. And when we compare something like intramolecular forces, like covalent bonding, like ionic bonding, those are always much, much stronger than an intermolecular force. And we know that from just a very simple thing that we've all done, which is we've all heated water up. And when we heat water up, the first thing that happens is actually the bond between water molecules actually breaks, which is that intermolecular force. That allows this water molecule, for example, and this water molecule to go into the gas phase. If it was opposite, and the intramolecular force, like the covalent bonding part of it, was weaker, when you would go heat up water, you would start breaking these bonds and you would have alphabet soup, hydrogen gas, oxygen gas being formed, and there would be no pasta for dinner as that boiling process would not be a great deal. So this does not happen when you heat something up because intermolecular forces are much weaker. That bond between molecules actually is the first thing that breaks. And that is pretty much how most molecular compounds are basically held together. A bunch of them together are held together by these intermolecular forces. So it just takes a mild amount of heating, like to 100 degrees, for example, in the case of water, and you could get them to break apart and go into the gas phase very, very easily. So the general rule is the stronger the attractive force between molecules, the less likely it would be found in the gas phase. That's, for example, something like this, which is organic, also nonpolar. This type of molecule and a lot of the very early organic sort of molecules, methane, propane, butane, you might be familiar with those. Those are all gases under normal conditions. Because they are nonpolar molecules, what happens is when like a methane molecule and another methane molecule are held together, they're also held together by an intermolecular force. And it's what is known as a dispersion force, which we'll talk about in a later chapter as well. But dispersion force is probably the weakest sort of intermolecular force you could have. So it's such a weak force that pretty much you look at it wrong, it's just going to want to kind of break apart. And that's why they're sort of found in the gas phase under normal conditions. So if you're looking at something like methane, it's held together by a fairly weak intermolecular force, and it's found as a gas under normal conditions. Now, substances that are found as gases under normal conditions, we have a lot of those diatomic molecules, which are elements. We have our hydrogen, our nitrogen, oxygen, fluorine, and chlorine. They again exist, as we talked about, as those diatomic molecules. They are still elements, and now they are naturally found as gases. In addition, ozone, which is O3, is a gas. And of course, obviously, group 8 on the periodic table there, which is our noble gases. The difference between, say, noble gases and these are they are monoatomic, which means they come as ones, basically. So just helium and nitrogen, argon, and so forth. They don't come as diatomic molecules. And that's what we see here. Again, everybody in blue is under normal conditions. Everyday conditions are usually found as gases there. Let's talk a little bit about some of the characteristics of gases. Gases assume the volume and shape of their container under sort of ideal conditions, as we'll talk about. The idea is the gas molecules are basically flying around in the container they're in. Because they're constantly moving, it's thought that they fill the container uniformly. Gases are the most compressible matter, state of matter. Gases do mix evenly and completely, even in the same container. And again, just by the notion of gases, if they are in the same container, they are flying around, which means they are constantly mixing with each other as they're all in the same container and flying around and mixing. Gases typically will have a much lower density than liquids and solids. So when we talk about density for liquids and solids, usually is grams per milliliter. When we talk about the density of gases, usually the units are grams per liter. And we'll talk about calculating density of gases in this chapter as well. But again, the units typically for gases are more grams per liter than grams per milliliter in that particular case. Now, one of the most common sort of properties of gases is pressure. And one way that we measure a pressure is by what is referred to as a barometer. This is sort of a classic barometer, which is no longer in most schools as it contains mercury in most classic situations. But typically it is a pool of mercury and a column. And basically, as atmospheric pressure exerts on the pool of mercury, the mercury rises there, yeah, in the tube. And that is a very common way that we can calculate the pressure of a gas or pressure of the room, for example. And there are a few different units of pressure. 1 Pascal or kilopascals are sometimes used for pressure, and that equals 1 Newton meter squared. Probably this is the 3-pack of units that you see most in chemistry in terms of units, and that is 1 atmosphere is equal to 760 mmHg. That is millimeters of mercury. And that unit is because usually on a barometer, there's like a ruler on the outside. And you basically read the ruler. A lot of times it's in inches of mercury, centimeters of mercury, or millimeters of mercury is typically how you would read it, just like a ruler. Mercury, again, as we might have talked about earlier on, is an unusual substance. Mercury will actually have a sort of reverse meniscus. It will actually go in this direction. And if it is mercury and you read it, you actually would read from the top of the meniscus in that particular case if you do come across a mercury sort of barometer. And another unit of pressure is 760 torr, named after the guy who invented the barometer, Torricelli. And that is a conversion factor as well. That 760 is an important conversion. Basically, if you have atmospheres and you want either millimeters of mercury or torr, you're going to multiply by 760. And that will give you millimeters of mercury or torr. And vice versa, if you have millimeters of mercury given to you, or torr, and you want atmospheres, you're going to divide by 760. That is because another really important relationship is a millimeter of mercury will equal a torr. So it's a one-to-one relationship between those two units. So basically, you just change the unit. The number will stay the same if you're going from millimeters of mercury to torr. 1 atmosphere is equal to 101,325 pascals, or 101.3 kilopascals. There are some other units of pressures that you sometimes come across. A bar is a unit of pressure. A bar is equal to like 1.10 atmospheres. PSI, pounds per square inch, right? 14.7 equals a atmosphere there. But again, like I said, this is probably in chemistry the three very common units of pressure that we deal with probably the most: atmospheres, millimeters of mercury, and torr. And I would say in a lot of cases, not always, but in a lot of cases, you are a lot of times converting things into atmospheres is a very common conversion. So that 760 number is really important to remember. Now, pressure does change as obviously the distance from sea level increases. And as you can see, as you get higher in terms of that, the pressure starts to decrease. Why they pressurize planes, right? When they fly around and stuff like that. So we're going to talk about gas laws here. And we're going to see a number of gas laws. But when we talk about gas laws, there's three sort of variables that we deal with: pressure, volume, and temperature. And in a lot of these gas laws, sometimes we will kind of vary two of them, keep one constant. Sometimes we may vary all of them together. But these are the three sort of common areas of gases that we deal with: the pressure, the volume, and the temperature. And depending on sort of what is held constant, what is changing, there are different relationships that happen for each of these sort of variables. One way that you can look or sort of measure a gas is measure it using a manometer. And here, basically, the idea is you have this gas, it moves the mercury. This is sort of a closed sort of system here, as the top of it is closed. So that would be in a vacuum, which means the height of the mercury in the column will basically equal the pressure of the gas. Now, you could also have a situation where you have more of a open situation here. That also would then bring into account the atmospheric pressure pressing back down on it. So you do have to take that into account. And that's why the pressure of the gas in that situation would be really the pressure or the height of the column of mercury, and also the pressure or the atmospheric pressure in that particular case as well. So kind of a sort of a closed system and an open system. We'll do something similar to this in a sense when we do an experiment a little bit later on, where you have to do some measurements of the height of the water, for example, in your container. All right, so let's take a look at really the first sort of relationship, which is really our friend Boyle's law. And Boyle looked at the relationship between pressure and volume. He held temperature constant. And what he really saw was, as you can see in these sort of containers here, is as the pressure goes up, the volume typically will go down. So this sort of opposite relationship. And if you just think about it, for example, just logically think about it, if you have a really small volume, for example, where you have your gas molecules in, there's going to be a fairly good chance of it's not going to take very long for those gas molecules to fly around and start colliding with something. There's not a lot of room to fly around in. So as they're flying around, they're going to probably hit the walls of the container pretty quickly. That's going to cause an increase in collisions. So we will see an increase in collisions, and that's going to result in why we do see our pressure to go up in this particular situation. He also found sort of the opposite there. As the pressure goes down, that typically sort of correlates to the volume increasing. So if you just think about it logically as well, you have now a much larger volume for my, say, 4 gas molecules to fly around in. It's going to take longer for collisions to occur. It's going to take longer for them to hit the sides of the container and all that kind of stuff. The result of that is we will start to see a decrease in the collisions. And because of the decrease in the collisions, we will also start to see the pressure go down. And that's what we see when we look at sort of the tubes here. Here we have a much larger volume and obviously a much smaller column of mercury, right? As the volume gets smaller, we start to see a rise in the amount of mercury in the tube. And as we get even smaller in terms of the volume, we see a much greater rise in the mercury, which will result in a higher pressure in that particular situation. So that is Boyle's law, and that is basically P1 V1 equals P2 V2. This is what is known as Boyle's law, and this is at constant temperature. And a sort of interesting sort of relationship that comes out of something like Boyle's law is this. As we can see here on the graph on the left, at a much smaller volume, we have a much higher pressure at that smaller volume. Again, when the volume gets larger, we have a much lower pressure happening. There is a relationship that if you were to take any pressure volume relationships that you find in a Boyle's law situation, and you take that pressure and its corresponding volume type of measurement, it will always equal a constant number. And that's sometimes referred to as a little k, sometimes referred to as a proportionality constant, which means you can take a bunch of sort of Boyle's law measurements of pressures and the corresponding volumes. And all those measurements, if you multiply the pressure times the volume, it will always equal the same number. And because of that situation, that it will always equal sort of the same number, that is why we could kind of set them equal to each other and get this sort of before and after type situation happening here. And we get where it is again, our Boyle's law, P1 V1 equals P2 V2. Again, as the pressure goes up, volume goes down. Pressure goes down, volume goes up in this situation. Now, in terms of the pressure in this particular formula, it doesn't matter what the unit is, as long as it is the same on both sides. So if it's atmospheres on one, it should be atmospheres on the other. If it's millimeters of mercury, it should be millimeters of mercury. Same thing with the volume here. It really doesn't matter what the volume unit is, as long as it's, again, the same unit on both sides, so everything cancels out correctly. You could take a pressure over 1 over the volume, and you get this linear relationship in terms of Boyle's law. All right, so why don't you try one here? A sample chlorine gas occupies a volume 946 milliliters at 726 millimeters of mercury. What will be the pressure if the volume is set to 154 milliliters? Let's take a moment and see what you come up with here. Although we already have one gas law so far to choose from, that will shortly change. We will have a bunch to choose from. Obviously, we have Boyle's law here, but a really good idea when you are dealing with gas problems, and obviously you have a bunch of gas laws to choose from. A lot of times it's really good just to kind of pull out the information from the problem and label it as to what it is as a pressure, volume, or temperature. And a lot of times that will kind of point you in the right direction if you're not sure. So we have a volume here, just 946 milliliters. We have a pressure that's 726. millimeters there of mercury. We're looking for another pressure here, and we have a volume that's 154 milliliters. So very quickly, just by labeling it, you can kind of see Boyle's Law hanging out there. Doesn't matter truthfully which ones you call ones and twos. It doesn't, as long as you keep sort of the information that goes together. Most people just call the first information ones and the other ones twos. Now, unit-wise, we just need to make sure we're in the same units, so we are. In this case, when we do solve for pressure, we will end up in millimeters of mercury. Also, to rearrange this equation, not too difficult, but in general, gas law equations, pretty much when you move something to the other side, it ends up in the opposite location. So we're looking for this guy. So this guy's up on top, so we move it to the bottom to the other side, which is basically dividing it to the other side. And that would give us that P2 is equal to P1 V1 divided by V2. Putting in our numbers here, we will end up with 726 millimeters of mercury. Our V1 there, 946 milliliters divided by our V2, 154 milliliters. Here again, as long as we're in the same units, they will cancel. Will leave us with millimeters of mercury as our unit. And that's going to get us there. 44, we'll call it 60 millimeters of mercury in this particular case. First off, any question on the calculation there? Now, in addition, knowing sort of the relationships that occur with these gas laws could also help you make sure that maybe you didn't mess up on the calculation or something like that. What we see here in terms of the volume is it went from 946 to 154. That means my volume decreased. That means what I should see in my pressure based on Boyle's Law is an increase in pressure, and it went from 726 to 4460. So it did increase. So it did move in the correct direction. And that's a good way sometimes to sort of make sure you didn't maybe transpose a number or mess up on the calculation. Any questions on that there? Not to say it will catch every mistake, but it can be very helpful. All right, let's try another one here. An inflated balloon has a volume of 0.55 liters at sea level at 1 atmosphere. It goes to 6.5 kilometers where the pressure is 0.4. Okay, so once again, I'm just going to pull out the information. So I got a volume here of 0.55 liters. 1 atmosphere is a pressure. 6.5 kilometers is useless information in terms of this problem. We got a pressure of 0.4 atmospheres. And obviously here we are looking for a volume. So again, if you're not sure, you can hopefully be able to see Boyle's Law kind of in there as you pull out the information. And in this case, I'm going to call this ones. I'm going to call this guy twos. Once again, we do want to check units. So we do have atmospheres on both of those. So we're good to go in terms of that. In this case, it just means when we solve for volume, we will be in units of liters, which is okay. So we're going to solve for V2. That means we're going to send P2 to the other side there. And again, going to end up in the opposite location. And that will give us V2 is equal to a P1 V1 over P2. Make sure we put our numbers in the correct locations. That is 1 atmosphere. That is 0.55 liters, all divided by 0.4 atmospheres. Atmospheres will cancel, going to leave us liters as our unit. And that is going to leave us a 1.4 liters in this particular case. Once again, we can think about sort of the relationship that we're looking at. Here, our pressure started at 1 atmosphere, went to 0.4, which means in this case, my pressure went down. I should expect my volume to go up. It went from 0.55 liters to 1.4 liters. So the volume did go up, so that is good. Again, if you see your volume going down, you probably, inverted some numbers or something of that nature. Any questions on Boyle's Law here? So again, pressure, volume, temperature constant. And again, as one goes up, the other goes down. And that is the relationship. So the next sort of gas laws we're going to look at is involving a couple of things, and one's going to involve volume and temperature, holding pressure constant, and another one's going to be pressure and temperature, holding volume constant. So this is really, as we'll talk about in a second here, Charles' law, and this is what is referred to as Lussac's law. And we'll start with sort of the pressure and temperature relationship and holding the volume constant and what we would expect to sort of happen in that situation. So, for example, if we have a gas molecules in this container and the volume is pretty much constant, it's not going to go up, it's not going to go down, it's basically going to stay the same. And we have some gas molecules in there. And if we increase the temperature in this case, we would expect our gas molecules to start moving around slower or faster if you increase temperature. Temperature should make the gas molecules move much faster, right? Like lighting a fire underneath somebody. So we should expect these gas molecules to start flying around a lot faster within this container. And because they're going to now be flying around a lot faster within this container, in this volume that's not moving, it's going to cause really an increase in collisions. So we would expect an increase in collisions in this case. And because of that, we would also expect the pressure to start to go up because, frankly, the volume stays the same, things are moving faster, and take a shorter period of time for collisions to occur, and that will result in a lot more pressure. Now, if we take kind of the same situation here, bad drawing container here, and we do the opposite, which is we actually decrease the temperature. So when we decrease the temperature, what we would expect to happen is our gas molecules should actually start flying around a lot slower. So they actually should slow down. And what that means is as they're moving around this container, they're going to be moving, dramatically drawn here, much, much slower, basically, right? And because they're moving around much, much slower, it's going to take a much longer time for collisions to occur. That's going to actually result in a net probably decrease in the amount of collisions that are going to occur. And we would expect the pressure in this case to also start to drop as a result of that. So in the case of Lussac's law here, as we increase the temperature, we would expect more collisions. More collisions will result in an increase in pressure. So as one goes up, the other goes up, and vice versa. As one goes down, the other goes down. So as the temperature goes down, everybody moving around slower, less collisions, less pressure. And that is sort of the relationship that we see in a Lussac type situation where the pressure is, I'm sorry, the volume is constant. Now, if we look at sort of a Charles law situation here on the left where we have volume and temperature, but the pressure is constant, what happens in this situation is if we take our container and we increase the temperature like we did before, what is going to happen in a situation where the volume stays constant, we would expect an increase in pressure as we just talked about. But in this case, we actually want to keep the pressure constant. So because we are increasing the temperature, we're going to get our gas molecules again to fly around a lot faster. But what happens to allow it to basically maintain the pressure as being constant is because the gas molecules are moving faster, we need to increase, dramatically drawn here, the volume. So we see the volume will increase. The result of that is even though that the gas molecules are moving faster, the volume increases. They now have a lot more room to fly around in. What that does is keep the level of collisions about the same as it was before. And that's what's going to allow it to basically maintain its pressure and keep the pressure constant. So even though the gas molecules are flying around faster, they have more room to fly around in, and thus the number of collisions stay the same and the pressure stays the same. The opposite is true if we take that same sort of situation and we decrease the temperature, our gas molecules are going to move around a lot slower. And the result of that, as we saw over here, is if the volume stays the same, the pressure will start to drop. So what happens in this situation is, frankly, we squish everybody down. and we start to see a decrease in the volume, and the volume will go down. The result of that is because the gas molecules are now moving around slower, by squishing them together, they now don't have any longer of a traveling path that they need, and that will keep the number of collisions basically being the same. So we kind of decrease the volume, keeps the collisions constant, and that's what keeps the pressure constant. So in a Charles Law situation, what we have happening is what is able to keep the pressure constant is the volume of the container actually adjusts to allow the pressure to remain constant. So you got like a movable piston type thing. It goes up and down. You know, you can change the volume of a particular container. We don't get that in the Lussac situation because the volume is fixed, and thus it will not basically adjust. And we do see the pressure go up or down when the temperature changes. So in Charles' law, as the temperature goes up, the volume goes up. And as temperature goes down, the volume goes down. Any questions on that there? And that's what we see here in this container at a low temperature. We have a lower volume of gas, and at a higher temperature, the gas needs a lot more room to move around in, and you have a much higher sort of volume of gas in that particular case. Now, there is also an important relationship when we talk about these formulas, are these gas laws, which is interesting. If you take a graph of volume versus temperature for any gas that you like, any different gas, and you draw these sort of best fit straight lines and you extend the lines to the temperature scale, the temperature scale always hits the same value, which is minus 273.15 degrees Celsius. Minus 273.51 degrees Celsius is a number that should look familiar to you. That is the number that we use to convert to Kelvin, 273.15. And Kelvin recognized that and called that absolute zero. That's because if you convert that to Kelvin, you add 273.15 and you end up with 0 Kelvin, which is absolute zero. So Kelvin recognized the nature of this. You can take pretty much any gas, extend it out to the temperature line, and it will always hit the same temperature value. The result of that is when we are dealing with pretty much gas laws, and we are looking at a couple of gas laws, which, by the way, here are Charles' law, is what we see there on the bottom, V1 T1 over V2 T2. And again, this is at constant pressure. I'm sorry, not constant pressure. Constant pressure. And that is, again, as the temperature goes up, the volume goes up, temperature goes down, volume goes down. And if we look at Lussac's law here, which is basically P1 over T1 is equal to P2 over T2, and this is at constant volume, where we see the pressure goes up, the temperature goes up, and the pressure goes down, the temperature goes down. Whenever you have in any gas law, essentially, temperature, they need to be in Kelvin. So if you're doing any type of gas law situation, any type of one that involves temperature, you do need to convert the temperature into Kelvin 100% of the time. Again, you need to add 273 to it. This also includes problems which sometimes confuses people, which is they will give you temperature and say Celsius, and they'll ask you for the answer in Celsius. So people think I don't need to do any type of conversion. I could just leave it in Celsius and go into the gas law, and you will get the wrong answer. So even if they give it to you in Celsius, want the answer in Celsius, when you put it into the gas law, it has to go into Kelvin and then into the gas law, and then you have to convert it out of Kelvin at the end to get to Celsius. So that's a very common mistake that people make, is when they see problems like that, they think they never has to kind of convert it because they want the same unit at the end. So without thinking about it, if you're using a gas law and its temperature, just like automatic, probably the first thing you should always do is just convert the temperature into Kelvin, and you'll usually be in good shape. Any questions on any of those there? All right, so let's try one here. Sample carbon monoxide occupies 3.2 liters at 125. What will be the temperature at the volume of 1.54? Okay, so let's take a look. Once again, I'm going to pull out the information. So I got 3.2 liters. That definitely is a volume. It's at a temperature of 125 degrees Celsius. I am looking for another temperature value, and I have another volume given to me at 1.54 liter. So again, now we've got a few gas laws to choose from. Obviously, there's no pressure here, so that eliminates Boyles, also eliminates Lussac. So hopefully, again, you could kind of see Charles' law sticking out at you there. I'm going to call these guys ones, this one twos. So V1 T1 equals V2 T2. Remember, automatic here, we got a temperature, so just going to automatically convert that into Kelvin, which it does need to be in this particular case. And that's at 398 Kelvin. Units here for my volume. And once again, you do want to make sure they're the same unit. And in this case, they are. They're both liters. So we're good to go. In this case, we are looking for T2 in this case, I believe. So remember, again, opposite as you cross over the equal sign, which means that this guy is going to end up on top. Also means I do need to move this guy to the top and this guy to the bottom and rearrange everybody in that aspect. So basically T2 here is going to equal V2 T1 V1. And once again, what we're really doing is we're multiplying T2 to the other side. We're then going to multiply T1 to the other side and divide by V1 to the other side. And that will get us where we ended up. Again, or just move everybody to opposite locations as you go across the equal sign. We want to make sure we get everybody in the right spot here. So it looks like a 1.54 liters up on top. We have a 398 Kelvin, and that's going to be divided by a 3.2 liters here on the bottom. Liters will cancel. Going to leave us Kelvin in this case, so 1.54 times a 398. That's not 398. Try that again. 1.54 times 398 divided by 3.2. And we'll call it a 192 the Kelvin in this case. And in this particular case here, if you wanted it in Kelvin, we could subtract 273, and we're actually looking at a negative 81.5 degrees Celsius. Now, again, in this situation here, we see that our volume started at 3.2, ended at 1.54, so the volume went down. This is Charles' law. That means my temperature should decrease as well, and it did. It went from 398 to 192, so the temperature did go down, again, in the correct direction. Any questions on that one there? All right, we will lay it up there.